Welcome to A-Level and EP Physics. In today's lesson, we will discuss past paper questions from May June 2025, Paper 4, Variant 4. As always we will discuss these questions in detail so you can improve your conceptual understanding of physics and also you can have better understanding of these exam questions. Let's study together, let's improve together. In question 8 says, an incomplete circuit diagram of a bridge rectifier is shown in figure 8.1. Complete figure 8.1 for the bridge rectifier such that the point A is set at positive potential with respect to point B. So this one has to be positive, this one has to be negative. So how we can draw the diodes? We need to draw the 4 diodes. So one thing you need to understand is that I often used to tell students the side where diodes converge, that is positive. From where they diverge, that side is connected with negative. So diverge, so diverge means this means diverge, this means diverge, and this means converge. So if you have this understanding, now you can draw the diodes. So this is simply how you need to draw. This has to be complete, no gap in your diagram. Diverge, so here these two, they have to diverge. So this is how you can draw, they have to diverge. So we can draw here, diverge. So here they have to converge. So this is how you can draw, they have to converge. So here also has to converge. So we can draw, they have to converge. But there shouldn't be any gap. So this is how you need to draw. So you can also see when this side is positive, how current will flow. It will flow this way, but it cannot go this way because this is in reverse biased. So current will go this way. It will pass through this one, then it will enter resistor from this side. So the entering side of the resistor is positive. So it will flow like this. Then it will go like this, and at this point current cannot flow this way because this point is at high potential and this point is at low, and current cannot flow from low to high. Always current flow from high to low. So current will not go this way, so it will pass through this diode and come back. So simply you no need to draw these dotted lines, so you need to draw these 4 diodes. Part B says the variation with time t of the potential difference V across the load resistor is shown in figure 8.2. The capacitor is now connected between points C and D of the bridge rectifier. This results in a smoothing of the PD across the load resistor. The difference between the maximum and minimum values of the smoothing PD is 33% of the peak value. On figure 8.2, draw a line to show the variation of the PDV across the load resistor with time t. We need to draw at least from here to here. So the difference between maximum and minimum is 33%. So 100 if we divide into 3 parts, so we can say the V min, minimum value of V, this has to be equal to 2 by 3 of V naught, and the V max, this will be equal to V naught. So these are the points we need to understand. Now we can count the squares. So if you look at this point, we have 10 square here and 5. We have total 15 squares. So it means that 2 by 3 times 15 mean V naught is represented by 15 small square. So how about the V min? This will be represented by 10 small squares. So we can say 10 small square. So these are the points you need to understand to sketch the graph. So it means it will drop from here to this point. So it will drop like this. So let me draw in a proper way a little bit. So actually it's a curve, exponential decay. It will decay like this. Then it will rise. So here it will fall to this value, then it will rise, it will fall to this value, it will rise, then it will fall to this value, then it will rise, then it will fall. And so now simply we can, from here exponential decay, then here it rise to maximum value, then exponential decay, and then again it will rise to maximum value, then again exponential decay, and then it will rise to maximum value, and then again it will decrease, so somewhat here it will decrease. So this is how we need to draw. Second part says use your line in B1 to determine in terms of capital T, means in terms of time period, the time constant of the smoothing circuit. If you look at this diagram, we can see the maximum value is V0 and our capacitor is discharging here. You have to be clear, capacitor is discharging here, so we can say capacitor is discharging here from this point to this point. Capacitor is discharging, and then from here to here capacitor is charging. So this red one is representing capacitor is charging. To find the time constant, we can use this discharging part. So if we draw the line here at this point, so we can see the number of small squares, these are 11, and total number of small square for one time period, we have 10 here, we have 20 here, so 30, so we have 30 small squares. And the value of V after discharging of capacitor, means the minimum value, that is equal to 0.67 V0. This is 2 by 3 of V0. Now simply we can use the discharging formula. V is equal to V0 e to the power of minus t over tau. So what is the t here? Time taken from here to here. We can write on this one in terms of time period. So time period is equal to 30 small squares, and here we have 11, so it simply means that this is 11 by 30 of time period. So this is the time taken from V0 to 0.767 V0. So this time is t. Now we can simply plug in value. So here we have 0.67 V0. This will be equal to V0 e to the power of minus t over tau. But t we can replace with these values we have done. So we can simply say, in this case, this is minus 11 by 30 times capital T. And this V0 we can cancel with this V0. So simply we left with 0.67. This is equal to e to the power of minus 11 by 30 times capital T, and this is divided by tau. Now we can take natural log on both sides, ln, so we have 0.67 ln. So here ln is 1, so what we will get minus 11 over 30 times t, and this is divided by tau. We need to find out value of tau. So tau we can multiply on other side, so this is 0.67. So we can also write on this one tau. This will be equal to minus 11 t by 30 divided by ln. So here we have ln natural log of 0.67. So simply just basic mathematics. Now if we plug in values, we will get in this case 0.36 t. This is divided by 0.40, and if we simplify this one, we will get 0.92 capital T. So this is how we can find out value of tau. I mean, this is the time constant actually for the capacitor, discharging capacitor. This is how we can figure out. Third part says the resistance of the load resistor is now increased. The capacitance of the capacitor is unchanged. State and explain the effect of this change on the smoothed output PT. So what is the effect on output PT? Or we can say what is the effect on ripples. So for this one, as the resistance of this load resistor is increased and our capacitor is connected between C and D, so capacitor is connected here. So capacitor will discharge through this resistor. So tau for discharging is equal to RC. So if resistance increased, C remains constant, so tau will increase. Tau increase means that capacitor will discharge slowly. Capacitor discharges slowly. So what does it mean if capacitor discharges slowly? If capacitor discharges slowly, so we will see the curve somewhat like this. So this means capacitor is discharging slowly. So this will be the new curve. So we can draw like this. Capacitor is discharging slowly. So this is how curve will look like. So the ripples, you can see the variation in PD, it has decreased. First of all, variation in PD across load resistor was this much. This was the delta V, but now is just this much. So it means variations in ripple will decrease. Variation in PD decrease means ripples will decrease. So these are the points you need to understand to answer the question. Now let me show you the answer, how you can write down a nice answer. So in your answer, you have to include these points. So first of all, you can say as R increases, tau will be greater. As tau is greater, it means capacitor discharges slowly, so the ripples will decrease. Question 9 part A says, describe what is meant by wave particle duality. Wave particle duality means that waves can behave like particles. They can exhibit particle-like behavior, and particles like moving electrons, they can exhibit wave-like behavior. So this is wave particle duality. So waves, we can say they can exhibit like particle-like behavior. So we can say particle-like behavior, and particles can exhibit like wave-like behavior. So we can say particle, moving particles, very important one. Moving particles can exhibit wave-like behavior. Yes. American or UK, same. So behavior. So these are the points you have to write down in your answer. Now let me show you the answer. So in the answer, these points you have to mention. So if you have mentioned wave particle duality is the concept. Electromagnetic waves mean the waves can exhibit particle-like behavior, while moving particles can exhibit wave-like behavior. So this means light can act as a stream of particles, mean light consists of photons, and particles like electrons can diffract, they can interfere like waves. Second part says, state the relationship between the de Broglie wavelength of a particle and its momentum p. State the meaning of any other symbols that you use. So simply we need to understand de Broglie wavelength simply is equal to h over p, and p is the momentum of particle, and lambda is de Broglie wavelength, and h is Planck constant. So simply we have to say that h is Planck constant. So this is what you need to say. State the meaning. So Planck constant, and the value of Planck constant you also need to understand is 6.63 times 10 to minus 34 joules second. This is not part of answer, but simply you need to write down h is equal to Planck constant. Part B says an arrow beam of electrons all with the same speed is incident normally on a carbon film. The electrons then move on to a fluorescent screen as illustrated in figure 9.1. The apparatus is in a vacuum. The pattern produced on the screen is shown in figure 9.2. So here we have figure 9.2. Explain why the pattern in figure 9.2, very important one, why the pattern in figure 9.2 provides experimental evidence to indicate a wave nature for the electron. So first of all, we have to look at the pattern. So how this pattern look like? This pattern, we have concentric concentric rings. So we can say concentric rings, and these rings are formed due to spreading out of electrons. So we can say due to spreading out of electrons. So we can say due to spreading out of electrons. Spreading out. So it means that electrons have undergone diffraction and interference. Diffraction and interference. Diffraction and interference are only the properties of waves. So in this case, electrons behave like waves. Or we can say electrons have wave nature. Or they are behaving as waves. So these are the points we need to write down in our answer. If you understand these points, now let me show you how you can write down the answer. So we can say, first of all, concentric rings are characteristics of wave interference. This occurs because electrons behave as waves when passing through the carbon film, diffracting and interfering constructively and destructively. So this is how you can answer, and this question has 2 marks. Second part says the speed of the electrons is increased. Suggest with a reason how this change affects the pattern observed on the screen. I mean, how this pattern will change if we increase the speed of electrons. So first of all, we need to understand lambda, the wavelength, is equal to h over momentum of moving particle, means momentum of electron, and this is d wavelength. So here h divided by m times v. So if v increase, it means lambda has to decrease. So it also means that one more thing you need to understand, lambda is directly proportional to theta. If lambda decrease, it means theta also has to decrease. We can also understand from here, first of all, let's say this is our center fringe, first fringe, bright fringe, and this one is the second. Like this, let's say it is formed like this. But now when we increase the speed, how these bright fringes will form, in this how these rings will form. So first one may be formed here, and the second one will be formed here. So they will be closer to each other, so the angle will decrease. So this is the point you need to understand. Now let me show you the answer, how you can write down the answer. So this is what you need to write down for the answer of this question. You can mention this point. So first you can say higher speed, shorter wavelength. You can also give reference of this formula. So there will be tighter diffraction. So these are the key points. So if you write down, you will get the marks. If you want to explain a little bit more, why tighter diffraction? So this is because lambda is proportional to, theta is proportional to lambda. So if lambda is small, theta will be small. Question 10, part A says, describe how the piezoelectric crystal in a transducer generates ultrasound waves for use in medical diagnosis. Piezoelectric crystal, you can say. How ultrasound waves are produced. So if we have the crystal, so imagine that this one is the crystal, we can apply alternating PD across this one, alternating PD. And the natural frequency of this crystal is in ultrasound range. So the size, the dimensions of this crystal are very important. So when we manufacture this one, so we need to consider the dimensions of this piezoelectric crystal. So its natural frequency is in ultrasound range. So the natural frequency should be in ultrasound range, means greater than 20 kilohertz in ultrasound range. And when the natural frequency of piezoelectric crystal, natural frequency we can say, natural frequency about equal to the applied frequency of the voltage, applied frequency of the voltage alternating of AC. then resonance will take place and ultrasound waves will be produced. Resonance takes place. So these are the points we have to mention in the answer. Now let me show you the answer, how you can write down. So in the answer, these points you have to mention. First, you can say alternating PD has to be applied, as we mentioned here. So this is alternating PD to the crystal. When frequency of this applied potential difference matches the crystal natural frequency, resonance will take place. This means crystal will vibrate with larger amplitude. Means the maximum electric energy will go to vibrate the crystal. So the amplitude of the sound waves produced, ultrasound waves produced, that will be greater. The natural frequency of such crystal is designed to be in the ultrasound range, meaning the resonant vibrations produce ultrasonic waves. So when crystal is vibrating, so it will vibrate at the same frequency. So the waves produced, they are ultrasound waves, because the frequency is greater than 20 kilohertz. Part B says a parallel ultrasound beam is incident on the boundary between the two media, as illustrated in figure 10.1. The media have specific acoustic impedance Z1 and Z2. At the boundary, a fraction alpha of the incident intensity of the ultrasound beam is reflected. The remainder is transmitted. State what is meant by specific acoustic impedance. So first of all, we need to understand specific acoustic impedance. Z is equal to rho times C. So we can say acoustic impedance is the product of density of medium, very important one. You need to specify which density you are talking about. Density of medium and speed of ultrasound sound waves in that medium, or you can say speed of ultrasound waves in the medium. So this is how we can state what is meant by specific acoustic impedance. Second part says describe how alpha depends on the relative values of Z1 and Z2. So first of all, we can simply write on alpha is equal to Z1 or Z2 divided by Z1 plus Z2 square of this. So if Z1 is about equal to Z2, so what will be the value of the alpha? Alpha will be equal to 0. It means that minimum reflection means most of the waves, they will be transmitted. So we will say minimum reflection. So this is the first thing, minimum reflection. And the second case, what will be the value of the alpha if Z1, for example, or Z2 is much greater than Z2? We can also imagine, let's say Z2 is negligible. So what we will get here? If Z2 is negligible, then alpha will be equal to Z1 square minus, there will be 0, divided by, so let me write down in a better way. So we can simply say this will be Z1 minus 0 divided by Z1 plus 0 square. So what we will get in this case? Alpha will be equal to 1. So in this case means maximum reflection. Most of the ultrasound waves, they will reflect back. So we can say maximum reflection. So this question is very common one. So you need to be very clear how to answer this one. Now let me show you the answer. This question has 2 marks, so you can write down these 2 points. Maximum alpha is about equal to 1 when Z1 and Z2 are very different. And if they are almost the same, alpha is almost equal to 0. Part C says a parallel ultrasound beam of intensity I0 enters a region of soft tissue. After passing through a distance of 2.1 centimeters through the tissue, the intensity of ultrasound is 0.62 I0. Calculate the linear attenuation coefficient mu of ultrasound in the soft tissue. Give a unit with your answer. So in this case, simply we can imagine this one is a soft tissue. This is soft tissue. Incident intensity is I naught when it has traveled distance. Let's say it has traveled this distance inside this tissue. Intensity at this point is 0.62 I naught, and the distance travel is 2.1 centimeters. So we need to find out what is value of mu. So we need to find out what is value of mu. So for this one, simply we need to understand this is kind of exponential decay. I is equal to I naught e to the power of negative mu x. So we can also say this as a function of x for better understanding. But it is given to us when x is equal to 2.1 centimeters, or we can say here x is equal to 2.1 centimeter. If you use 2.1 centimeters, so your answer will be in centimeters. This convert this one into meters, your answer will be in meters. So it depends on which unit you are choosing. So you can use centimeters, you can use meters. So I'll be using centimeters. So let's use centimeters. So here we have value of I at distance of 2.1 centimeters, that is 0.62 I naught. This is equal to I naught e to the power of negative mu x. So I naught we can cancel, so we left with 0.62. This is equal to e to the power of negative mu x. Now we can take natural log on both sides. So we can take ln of 0.62, and ln of e is 1, so we will get negative mu times x. So we can simply say x will be equal to negative ln of 0.62. So if I use this one in centimeters, so I'm using 2.1 centimeters. So our answer will be equal to 0.23 per centimeters. So this is, you can also convert this one into meters. So that will be 23.1 about. So if you convert that, will be equal to 23.1 per meter. So we can write on here, this is 0.23 and the unit is per centimeter. So this is how we can answer. Question 11 says the deuterium nucleus has a mass defect equal to this. The helium nucleus has a mass defect of this. Helium-4 is formed from deuterium in a nuclear reaction that can be represented by the equation. So here we have deuterium nuclei. They combine together and they form the helium nucleus. Part A1 is asking us state the name of this type of nuclear reaction. So as in this case, deuterium nucleus combine to form the helium nucleus. So this is simply nuclear fusion. So we can say nuclear fusion. So this is simply, you need to write down, this is nuclear fusion. But I have written a little bit in detail, so I will show you a little bit detail as well. So maybe you need for your notes. So this is. Second part says, show that the energy released when one nucleus of helium is formed from deuterium is equal to this one. And in the last part, we have the mass defect. So we can find out delta M first of all. So we have deuterium and the mass defect for deuterium is 0.002388 U. This is AMU. And for the helium we have mass defect that was given in the last part 0.03037 U. And if we solve this one, in this case we will get 0.0232113 U. So we got the negative. It means the mass defect in helium is greater than deuterium. So it means energy will be released. So how we can calculate the energy released? Energy released, E will be equal to delta M times C square. But delta M has to be in kgs. So we can simply write down 0.0232113 times 1 joule. So we need to understand 1 joule. Atomic mass unit is equal to 1.66 times 10 to minus 27 kgs. So we can simply write on here 1.66 times 10 to minus 27 kgs multiplied by c squared, that is 3.0 times 10 to 8 square of this. Now if we solve this one, we will get 3.47 times 10 to minus 12 joules. So this is how you can find out. You need to understand how to calculate energy released based on given binding energies, based on given mass defect, and also based on mass defect by calculation. So mass defect will not be given to you. You have to calculate mass defect. So you will calculate the mass of reactants minus mass of products. So you can find the mass difference and then you can use the formula. So 3 ways you should be able to calculate energy released based on given masses, based on given mass defect, and based on given binding energies. So this question is based on mass defect. And also you need to understand individual particle like proton and neutron, they do not have binding energy and also they do not have mass defect. Part B says a star has a radius of 6.96 times 10 to 8 meters. Helium-4 is produced in the star from deuterium at a mass rate of 7.34 times 10 to 11 kgs per second. All the energy released from this process is radiated away from the star. All the energy that is radiated from the star is released by this process. Calculate the luminosity of the star. So what is luminosity of the star? Luminosity of the star is the power of the star, means all the energy radiated by the star per second, or you can say total power radiated by the star. And so how we can calculate the total power? If we have energy released per reaction, so I can say energy released per reaction, so we can say energy released per reaction, and if we multiply with this one with number of reactions taking place per second, so we can calculate power. So these are the points. Now energy released per reaction we have already calculated in the last part, so we can say that is energy released per reaction, that was 3.47 times 10 to minus 12. So this one we have. Now we need to calculate number of reactions per second. So how we can calculate this one? So I'll be writing here number of reactions delta n by delta t. So how we can figure out this number of reactions per second? To calculate number of reactions per second, it is given to us the mass release in 1 second. So simply we can say this is 7.34 times 10 to 11. This is kgs, we can say, per second. And we have mass per reaction. So if we divide this one by mass per reaction, so we will get reactions divided by mass per reaction used. This is mass per reaction, so I have written reactions over mass for your better understanding. So what is the mass of one single helium nucleus? So mass of single helium nucleus. So this one, if we want to write down second, we can write down mass of single helium nucleus. So we can say reactions. Mass is 4 times 1.66 times 10 to minus 27. This is the mass. So this is kgs per second, and this is also in kg. So this is also in kg. So kg cancel. You can see reactions per second we can figure out from here. Now if we solve this one, we will get 1.11 times 10 to 38 per second. So these are the number of reactions per second. So we can write on here 1.11 times 10 to 38 number of reactions per second. Now if we multiply these two together, we will get 3.85 times 10 to 26 watts. So this is the energy released per second. So this is how we can approach. So this is very important one. So try to understand the logic, what data is given to you, how you can use that data to find the answer. So this is, so here I have written number of reactions per second. We have mass per second, how many kgs are released in 1 second, and we have the mass released in one reaction. So I have written mass released per reaction. So you can also say, if you want to write down this one, you can also say this is 1 over, you can say, mass per reaction. So if you understand this way better, mass per reaction, and then we will get number of reactions per second, multiply, and we can find the answer. So the approach you need to understand. Second part says use the answer in B1 to determine the surface temperature of the star. So simply we have to use Stephen Boltzmann law for this question. Luminosity of a star is equal to A times sigma times T to the power of 4. So this is the surface area. So we can say luminosity, this will be equal to 4 pi r square times sigma times T to the power of 4. So we need to find out temperature. So this will be equal to luminosity divided by 4 pi r square times sigma, and the power of this one 1 by 4. Now simply if we plug in values, we can find the answer. So we have luminosity 3.85 times 10 to 26, and here we have 4 pi, value for r is given to us 6.96 times 10 to 8 square, and we need to multiply this one with Stephen Boltzmann constant, that is 5.67 times 10 to minus 8. Now if we solve this one, we will get about 5800 Kelvin up to SF. So this is our final answer. So this is how we can answer these questions. We have done this whole paper. I hope you have better understanding of these questions, and if you have any questions, please leave your questions in comments and I will try to answer as soon as possible. And if you're looking for more resources, please join Patreon. On Patreon you will see PDF solutions of these papers, topic-wise questions, revision summaries, and much more. And if these videos are helping you to improve your understanding of physics, please also share with your friends and your classmates. See you in next video.